Welcome back, guys. We're going to talk about a very exciting topic that is the mole. And we're going to do molar mass. We're going to try to do a little bit of dimensional analysis, some conversions between grams and moles, moles to atoms, and see how that works. So we've learned earlier that moles are like a grouping of different things. And so that's how we are able to keep track of all these stinking atoms because they're so small. So we know that 1 mole of something, for example, we're going to take a look at lead, right? A mole of lead right there is weighs 207.2 grams. Okay, 207.2 grams. So how much would 2 moles weigh? Well, it's probably 414.4, right? Does it make sense, right? You keep multiplying them. Doesn't that make sense? So essentially, that's what we're going to be doing here. So I said that 1 mole of lead was 207.2. So we're going to find the mass of 2.5 moles of lead. So we know 2.5 moles of lead, and we know lead is Pb, and the mass is our unknown, so mass is always in grams. So we'll start with what we know, 2.5 moles of Pb of lead, and then we are going to multiply by a conversion factor. We're going to put moles of lead on bottom, and we're going to convert to grams. All right. And that G right there, that G stands for go to the periodic table. You go to that periodic table, you'll look that number up. There you go, 207.2, and we're going to write 207.2 right there. You go to the periodic table for that number. That means that there are 207.2 grams in 1 mole. All right. So anytime you do a grams to moles thing, there's always a 1 in front of that mole. All right. Anytime it's grams to moles. Later, we'll do a mole to mole thing, and not necessarily going to be a 1 anymore. Okay. But this time around, that one's always going to be a 1. So kind of depend on that. 2.5 times 207.2, and so we end up getting 515 grams of lead, right? That made sense. I told you that 2 moles would be 414, is that right? Yeah, so 2.5 moles would be 518. So we'll do the same thing. We're going to now have a mass, 32.6 grams of sodium, and sodium is Na. And we're going to move to moles. Okay, so we're going to go the other way. You got 32.6 grams of sodium. And so let's go ahead and switch grams of sodium into moles of sodium. And you know what that G stands for? That's right. It stands for go to the periodic table. We are going to go and we're going to say it's 22.99. We're going to round that up and call it 23 grams per 1 mole. And that means that your calculator work is going to be 32.6 divided by 23. And so that's going to be 1.42 moles of Na. So if you're seeing that you are going from, if you're going from moles to grams, you're going to multiply by the molar mass. If you're going from grams to moles, you're going to divide by the molar mass. Okay? You could try to remember that if you really prefer it. I like to do the dimensional analysis because the steps will get longer. All right, and so I prefer to do it this way. So how many moles of atoms do you have if you have 2.7 times 10 to the 24th copper atoms? So that's a lot of atoms. Is it really though? Okay, so we're looking for the moles. So we have 2.7 times 10 to the 24th atoms of copper. And so we're going to convert, we're going to do atoms of copper into moles of copper. All right, sneak peek. Remember, up here at the top, we remember that it's equal to Avogadro's number. Remember, Avogadro's number is the number of particles, 6.02 times 10 to the 23rd. I know here it says 6.022, all right, but we're going to say 6.02 times 10 to the 23rd is equal to 1 mole, right? So 6.02 times 10 to the 23rd atoms for 1 mole. A for atoms, A for Avogadro's number. So your calculator work is going to show you that. Now, that can be tricky with scientific notation, so let me go ahead and show you how it's done here. The answer is going to be 4.5 moles. So you can skip this calculator work if you need to, if you're pretty comfortable with it, but let me show you how the calculator goes. It's going to be 2.7. And then we're on the TI-83. We're going to take advantage of this EE button. That's that comma that's right there. You have to push the second comma, right? And that will give you the engineering exponent, which is times 10. So whatever I put in after that is times 10 to the 24th. Okay? So that's 2.7 times 10 to the 24th. And now I need to divide it by Avogadro's number. So I'm actually going to hit the enter key just to be safe. And then I'm going to hit the divide button. And then I'm going to say 6.02 and then EE23. Okay? And there we go, 4.5, right? Here's the Inspire, in case you've got one. Here we go, it is 2.7. And then I'll do times 10 to the 24th. And then I will divide, and then I will put it in parentheses, 6.02 times 10 to the 23rd. Now the times 10 thing, I'm hitting the button that's next to the 1. That's 10 to the x. You don't need to mess with this root or this caret right here. You don't have to do that because we're always doing times 10. So that's the way it's going to work. And I hit the enter key. Now be careful, because if you do this and you divide by 6.02 times 10 to the 23rd like this, I did not put it in parentheses. Look what happens. See how that one is different from the one before it. It yanked that 10 to the minus third outside, which is now multiplying instead of dividing. And so that's why I've got a huge number over here. So that's not good. You can avoid this by pushing Control Divide, and that will give you a fraction, and that gives it to you in baby steps. You can't even, it's idiot proof. You can't mess it up. Okay? All right, piece of cake. Now the next one, number 4, how many atoms are in 0.5 moles of calcium? Okay, A for atoms, A for Avogadro's number. So you put Avogadro's number in here, and then for 1 mole, 0.45 times Avogadro's number is going to be 2.7 times 10 to the 23rd atoms of calcium. So you may ask, is there a reason why you're putting calcium here? I mean, couldn't you say the atoms of copper, right? Or atoms of lead or oxygen or whatever? Yes, it doesn't exactly matter because you're always going to use Avogadro's number. Avogadro's number represents any quantity. It could be eggs, could be paper, could be anything, right? Pencils, elephants, no big deal. All right, flip it over. Now, number 5 is going to ask us to go from grams. We're going to give in grams of iron, and we're going to change to atoms. So now we're going to start doing 2 steps. We're going to do grams of iron. We're going to change grams of iron into moles of iron. So you can go from grams to moles, and then you can go from moles to atoms. All right, and then you can go the other way too if you want. Now, so for iron, that is 55.8, if you'll look at that, 55.8 on your periodic table. All right. And then for 1 mole, and then we'll do moles to atoms. And that's 6.02 times 10 to the 23rd. I didn't leave enough room. Oh no. And so what you'll do is you'll do 3.65 times 6.02 times 10 to the 23rd divided by 55.8. That is going to give you 3.94 times 10 to the 22 atoms. Let me show you how that's done on the calculator. You're going to take 3.65, you're going to multiply by Avogadro's number, and then you're going to hit the divide key for 55.8. You don't even have to hit enter. You hit multiply for everything that's on top, and then you hit the divide for everything on bottom. I'm obviously excluding the ones. I hope I didn't mention that earlier, but that's what's going on. So answer is 3.9 E22, or times 10 to the 22. All right, let's do one last one. We've got atoms of neon. So 6.75 times 10 to the 19th atoms. So that's slightly less than a mole. So our answer should be less than what's on the periodic table. Atoms to moles. I did not leave enough room again. 10 to the 23rd atoms to 1 mole. And then I'm going to convert moles of neon into grams of neon. Right there. And so that, I'm doing this so my units cancel, right? Moles, moles. And then I'm left with grams. So I look at the periodic table. G stands for go to the periodic table. I go to neon. That is 20.2. Yep, 20.2. That's how many grams are on 1 mole. So now I'm going to plug that in the calculator again and get less than a mole again, 0.00226 grams of neon. So that is less than what's on the periodic table, less by kind of a lot, actually. So hopefully that works. I hope you guys enjoyed that. We're going to be doing this quite a bit, so make sure you've got this down pat. So one quick trick up here. You know how I said you could go from grams to moles and then moles to atoms? Well, just so you know, you cannot go from grams to atoms. Doesn't work. Not going to happen. All right. You can only go from grams to moles and moles to atoms. Now, you can go from atoms to moles and moles to grams too. To go from grams to moles, we use that molar mass, right? MM. Okay. Just abbreviating that. And then from moles to atoms, we use that number. We use Avogadro's number, right? Okay. So now, real quick trick, if you remember this little mole map that we have, you divide going in. So that means to go from grams to moles, you need to divide by the molar mass. And then you multiply out. So to go from moles to grams, you are going to multiply by the molar mass. Okay? Or to go from moles to atoms, you are going to multiply by Avogadro's number. To go from atoms to moles, you are going to divide by Avogadro's number. To divide by Avogadro's number. Okay, that is a quick trick. It's not something you should use as a crutch, but it is a cool trick. Let's now take a look at the mole calculations for compounds. So we've learned earlier how to find the molar mass of a compound. Remember, we learned that calcium nitrate was 164 grams per mole. We just looked up calcium, nitrogen, and oxygen. We multiplied by their respective numbers of each, and we added them all together. You remember doing that? And we learned. So we're going to have to do kind of the same thing here. What is the mass of 0.75 moles of magnesium chloride? So 0.75 moles of MgCl2. Well, I just need to do a quick tally right here. I know that Mg is 24. I look on the periodic table. Yep, Mg is 24. And then Cl is 35.5. So I'm going to add 2 times 35.5. If you approximate those, it's not going to make that big a difference. And so your molar mass is 95 grams per mole. So now that's all done. Now we can convert moles into grams, just like so. Moles, we're doing the units on top and the units on bottom to cancel out. We got 95 grams on top and 1 mole on bottom. And so 0.75 times 95 is 71.25, which is approximately equal to 71 grams, taking in account of our Sig Figs, because we have 2 Sig Figs. So you see how everything is kind of starting to build on each other? All right. Hope you were paying attention earlier. So now we have 204 grams of phosphorus tribromide, okay? And we want to know how many moles there are. So there are 204.0 grams of phosphorus tribromide. Oh, yeah, you remember that? That was a covalent compound. So there's 1 phosphorus and 3 bromines, right? Tribromide. And so we need to find the number of moles. So we're going to take grams to moles. G stands for go to the periodic table. We're going to look at phosphorus. Phosphorus is going to be 31, and then bromine is going to be 80. Okay, so we're going to do 31 plus 3 times 80, and that's going to give us 271 grams per mole. I used the inverse one. I hope that doesn't bother y'all. That should be grams per mole. So that's going to be 271 grams per 1 mole. And so that's going to end up being 0.75. I didn't do enough decimal places on my answer key. 204 divided by 271 is going to be 0.7528, okay, moles. PBR3. Just a word on Sig Figs. I don't know if I mentioned this yet. You're going to keep the same number of Sig Figs as your original answer. You're not going to look at the Sig Figs that are in your molar mass. You're going to assume that those are exact numbers, so their significant figures are considered infinite or not considered. Now, we want to say how many molecules are in 45.2 grams of water. So 45.2 grams of H2O. H2O we'll figure out. It's pretty easy. There are 2 hydrogens, and then hydrogen is worth 1. It's got 1 gram per mole. And then there's oxygen is worth 16. So 2 plus 16 is 18 grams per mole. So 45.2 grams of water, and we'll convert grams into moles. So 18 and then 1. And so 45.2 divided by 18. Oh, gosh darn it, we need to find molecules, don't we? Okay, so we need to go ahead and go one more step. We need to convert moles into molecules. Now, molecules is the same as atoms, right? Remember, atoms doesn't exactly matter. Avogadro's number is just a grouping of whatever particular thing. So it could be atoms, it could be molecules, it could be elephants. Who cares? So we're going to put Avogadro's number there. And so now that's going to be 1.51 times 10 to the 24th molecules. That's a lot of molecules. Now, the last one, what is the mass of 3.85 times 10 to the 24 formula units of calcium fluoride? So that's going to be 3.85 times 10 to the 24 units. I'm just going to say units. And then we're going to convert our units into moles. Now, formula units was the same as molecules, right? Formula units just means that it is It's an ionic compound. Okay, so it's the same, kind of the same thing as molecules. So 6.02 times 10 to the 23rd formula units in 1 mole. And then we're going to convert moles into grams, and that's calcium fluoride. And so I need to go to the periodic table to find that one. So calcium is going to be 40, and then fluorine is going to be 19. So it's going to be 40 plus 2 times 19. And so that means that it's going to be 78 grams per mole. So that's 78. And so 3.85 times 10 to the 24 times 78 divided by 6.02 times 10 to the 23rd, that will come all the way around to 499 grams of calcium fluoride. All right, thank you very much. Have a great day.